Let's take a look at the trends of boiling points. Unlike the melting points that we just discussed in the previous video, when you look at the trends of boiling points from the point of view of number of carbons present, of number of second row elements present in your molecule, you see a much more well-behaved, much more linear trends among the different functional groups, whether it's the alkane, the alkenes, the nitriles, the carboxylic acids, the amides. The trend looks a lot more linear than what we had before for the melting points. And this is once again a result of the fact that the molecules are now entering the gas phase, and they go from liquid to gas. There is no unit cell to which they belong entirely and they are constrained to. So they can be farther apart, and generally speaking, the distances between molecules tend to be a little bit more consistent from family to family. So now look at the boiling points. We're going to see if our prediction of the increase in intermolecular forces makes sense. And just to remind you, the greater the intermolecular forces are, the higher the boiling point should be. So we're predicting that the molecules, the alkanes, alkenes, alkynes, and aromatics should have the lowest boiling point when you compare them to molecules of relatively the same molecular weight that happen to be ethers, imines, or nitriles, which themselves will be lower than the carbonyl compounds, ketones, aldehydes, esters, and so on and so forth. So let's see if that really happens. Let's take a look first at the alkene, alkane, and alkyne families. And here in this graph, I'm also including the ethers because experimentally they happen to be very close, in fact, to each other. So notice what's happening here. The trend is actually very linear. That's phenomenal, right? You increase number of carbons or number of second row elements, and you see that linear increase. But if you start looking carefully at each one of these data points, you notice something rather peculiar. In particular, notice how the ether family, which is the red dots, right? So, or the red squares here, they start kind of high initially, right? On par with the alkynes. The alkynes and the ethers initially are kind of the highest, but as we go into higher amounts of carbon, the ether starts dropping down until ultimately ends up being the one with the lowest boiling point. Now, mind you, is not a lot lower than the alkenes, the alkynes, and the alkynes, but it is lower nonetheless. And so something rather peculiar is happening because we were predicting that this molecule being polar should in fact have a higher boiling point than the alkynes, the alkenes, and the alkanes. So we're going to investigate that in a second and see what's happening. But first, I want to focus on the alkanes one more time. And this time, I want to look a little bit more variety within the alkanes. Because we have the regular linear alkanes, the ones where, you're just going to go from left to right in your single, zigzag motion. But then there are other type of alkanes that are called the branch alkanes, the ones that, in addition to going, in that linear zigzag motion, you have these branched carbons sticking out of the main structure. And alternatively, you could even have the cyclic structures. Now, when you look at this graph, what you end up observing is that the linear alkanes tend to have higher boiling points than the branch alkanes. In fact, the most branch alkane here, the 2,2-dimethyl alkane, is the one that consistently has the lowest boiling point. The one that is, intermediate in terms of that branching is also intermediate in terms of boiling points, and the one that's completely linear is the one with highest boiling points. So we see that increasing the number of branching units within your linear alkane decreases your boiling point. But the other thing that's also interesting is that your cyclic structure happens to be consistently throughout the molecules that have the highest boiling point in the entire series. So let's try to explain this, like what is happening. Oh, and by the way, one more thing I should say is that the reason that your branch alkanes have lower boiling points is because they have less surface area. And if you recall from intermolecular force discussions, the lower the surface area, the lower the intermolecular forces. So this trend right here makes total sense in that regard. But what doesn't necessarily make a lot of sense is this difference between your linear alkanes and your cyclic alkanes. Like, what's going on? How come the cyclic alkanes have a higher boiling point? They're not as linear, I guess you could say, than your typical regular alkane. So what's going on? Well, this is what's going on. If you recall from your general chemistry part 2 classes, you may recall a formula known as the Gibbs free energy that tells you that the Gibbs free energy is equal to the enthalpy of a reaction or molecule minus the temperature times the entropy. And when you're looking at a particular phase transition, like a liquid turning into a gas, as in the boiling point, technically speaking, that happens at a point of equilibrium between the liquid and the gas phases. So the Gibbs free energy is zero because you are at equilibrium. There is nowhere to go, right? So there's no spontaneity going one way or the other. You are at equilibrium, so the value of delta G is zero. And what this allows us to do is solve for the temperature. We can actually solve for the temperature in this equation by moving the negative T delta S term to the right side, dividing both sides by delta S, and you end up with enthalpy over entropy equals the temperature, which in this particular scenario is the boiling point temperature. All right, so now let's take a look at these molecules. What we do see is that the alkane molecules are not restrained in terms of the structure. They can rotate every which way they want. They can rotate on their own axis. They can rotate on their own bonds. There's really not much of any restrictions in these molecules. They are free to move whichever way they want. The cyclic structures, on the other hand, they are definitely restrained and constrained as a result of being cyclic. You can break the cyclic structure, and so that creates some restrictions as to what can happen when this molecule rotates on its own bond. And in some cases, you just can't carry out with the rotation. So what this ultimately means is that the entropies of these two classes of molecules are different. The entropy of the linear molecules is going to be higher because you have the most options as far as bond rotation compared to the cyclic structures. And this is just your restricted rotation of cyclic structures kind of being represented from the point of view of entropy. But when you look at the formula here, that enthalpy divided by entropy, and we're going to make the assumption that between these two classes of molecules, the enthalpy is not very different. So we're going to treat it as a constant. The entropy of the linear structures is a lot higher than for the cyclic ones. So what that means is that your boiling point temperature is going to end up being lower for the linear alkanes because your entropy is higher compared to the cyclic alkanes, which have a lower entropy, giving you your higher boiling point. And the beauty of this argument is that just from thermodynamic arguments alone, that explanation and that concept, you can explain why the boiling points are different the way they are in these two classes of molecules. So it's kind of phenomenal. And might not be a bad idea to keep this type of concept in mind in the future. All right, so that explains what's going on with the alkanes. Now looking at, and already I mentioned to you that for the branch alkanes, the more branched you are, like in this case, the lower intermolecular forces you can actually have present, and as a result, the lower your boiling point is going to be. So we already explained all of that. This is also represented in the alkenes, by the way. You could have cyclic alkenes, linear alkenes, branched alkenes, and you see a similar trend altogether, which doesn't really change all that much. So the same argument can be presented to an alkene as it is for an alkane. The other thing too is that the alkenes can have the double bond at the end. They could have it in the middle of the molecule, and generally speaking, what we see is that they are roughly the same. There's not a lot of difference. In some cases, the alkene that's sandwiched inside of the structure ends up having a higher boiling point than the alkene that is terminal. And in other cases, the terminal alkene ends up being higher. So it kind of goes back and forth a little bit, but they are roughly in the same vicinity. So not a lot to be said there. But the ethers are kind of weird in the sense that they are having lower boiling points for the higher structure. So what's going on here? If you consider the structures of these two molecules, you can say, well, the oxygen is attracting electrons to it, the carbon is losing those electrons as a result of the electronegativity of the oxygen. So you create these delta pluses and delta minuses, these partial charges in the molecule. And for small molecules, this interaction is rather simple, definitely allowed, not a problem. Same thing with the alkynes. You have interaction between the pi bonds of those fragments. So you have greater interactions, greater attractive interactions, and higher boiling points. No problem. All right, but what happens if the structure becomes larger? Okay, so here is the issue. For alkanes and alkynes, generally speaking, not a huge problem because you're not changing the structure all that much. But in the case of the ether, you have those delta pluses and delta minuses. And the bigger the structure becomes for the carbon-carbon bonds, the less of a chance your molecules have of having the delta pluses and delta minuses coming close in contact with each other, and decreasing the chances for those positive and negative charges to see each other, the lower your intermolecular force of interaction is going to be. And as a result, your boiling point is going to suffer. And so this idea of kind of like saturating your molecule with hydrophobic portions, making it more hydrophobic than it is hydrophilic, it ends up kind of getting in the way. That steric hindrance definitely makes it less likely that you're going to be able to bring these things closer together, and the chances are kind of diluted to some degree, making it less likely that they'll see each other. So ultimately, your bigger ethers end up having lower boiling points. All right, so that's actually rather interesting when you start looking at the trends for making the molecules bigger and bigger. And hopefully you're appreciating that just from the discussion here. So we actually have to do a little bit of fixing in our tables. Now we're putting the ethers along with the other hydrophobic molecules, the ones that are only non-polar. Okay, so we're kind of beginning to rearrange things a little bit in this table. Now the next group in the experimental series are the aldehydes, the amines, the ketones, and the esters. And so we are actually kind of rearranging the table now a little bit. So we're bringing a few players, closer to the non-polar ends than we originally predicted, right? In fact, the only ones that kind of stayed the same were the carboxylic acid and the amides, which were always on the right side, right? And I guess you could say the same thing for the alkanes, the alkenes, the alkynes. All right, but let's take a look at this. So that carbon-oxygen double bond, the carbonyl group, it definitely gives you strong dipole-dipole forces, right? Which means that, yeah, you're going to have a higher boiling point than the preceding groups that we talked about earlier. The NH bond, however, even though it has hydrogen bonding forces associated with it, they're not as strong as oxygen-hydrogen covalent bond, hydrogen bonding interactions. So they kind of fall in part with this dipole-dipole force of the carbonyl group, and they're kind of like about the same. So you see a relatively similar aspect ratio for those molecules. Now the nitriles and the alcohols, that's kind of interesting because we didn't expect necessarily the nitriles to be this high. So what's going on? And they're relatively the same for alcohols and nitriles. Well, it looks like your nitriles, because they have that triple bond, you are creating a very, very strong dipole-dipole force. Strong enough that it actually kind of comes part to part with that OH hydrogen bonding of regular alcohols. So yeah, having double triple bonds actually increases your chances of how strong your dipole-dipole force can be, and in some cases like the one here, you can equate it to a regular hydrogen bond. Which brings me to the last set of groups, the carboxylic acids and the amides. They are at the top of the boiling point chain here. But the thing that initially, at least to me, didn't make sense is how come the amides happen to be the ones that have the highest boiling point? Why not the carboxylic acids? Because after all, the OH bond is a stronger hydrogen bond than the NH bond. So why are the carboxylic acids not higher in boiling point than the amides? And in order to answer this question, we need to take a look at resonance structures. So in the structures right here, I'm not drawing the lone pairs on each one of the oxygens. You have two lone pairs on the oxygens, and you have one lone pair on the nitrogen. If you bring the lone pair of the oxygen here to the carbonyl, you create the following resonance structure. Same thing with the nitrogen. All right, and when you look at these things, you could say, well, you're developing delta minuses and delta pluses on your carboxylic acids the same way that you're forming them in your amides. But the difference here is that your amides, which are made of nitrogen, nitrogen is less electronegative than oxygen. And so it has a greater tendency to dump electrons onto the carbonyl, or at least a lot more than oxygen does. And so the creation of these delta minuses and delta pluses in the amides is greater than it happens to be in your carboxylic acids. So you end up with delta pluses and delta minuses for a greater amount of time in your amides than you do in your carboxylic acids. And the result is that you end up with higher boiling points with the amide family in comparison to the carboxylic acids. So this kind of rearranges the entire set of groups in terms of boiling point by looking at experimental cases and using the experimental information to adapt our knowledge of intermolecular forces within the constraints that the organic molecules allow us to look into. And that could be changes in electronegativity, changes in resonance structures. It could even be a change in the overall shape of the molecule. So hopefully this allows you to get a greater insight into how intermolecular forces affect the chemistry, or in this case, the physical aspects of organic molecules. So let's end the video right here, and in the next one we'll talk about distillation.